All right, we're in Building 26 again, covering some really awesome tools.
Hi, my name is Baskar Sridharan. I'm a Senior Development Lead in the Windows Reliability Group. My team owns the development charter and the technology for detection, diagnosis, and recovery from certain classes of reliability failures. Radar memory leak detection, memory exhaustion detection, deadlock detection, the WinRE technology, that is the Windows recovery environment for automatically recovering from boot failures and from long-term performance degradation of the system, technologies for recovering applications from network hangs. These are examples of things that my team owns. So today we're going to talk about Radar.
Yeah. Cool name, by the way.
Oh, thanks.
You're welcome.
So Radar is a technology for automatic and live detection and diagnosis of memory leaks that happen on the field, on customer machines. So the primary focus of Radar was to be able to perform leak detection when the customer is undergoing pain. When the actual leak is happening on the customer machine, we want to do it then, not after the fact. So because of this, there are certain requirements, constraints that came into effect, and we had to put a lot of engineering effort into it to ensure that we could get this right. So for example, some of the key requirements that we had to work with, where we put in a lot of engineering effort, was we needed to make sure that Radar was really, really tiny in terms of the footprint, in terms of CPU utilization and memory utilization. Mm-hmm. Right? So today we use less than 1% of the CPU.
Nice.
And we cap our max memory utilization to a few megabytes.
Okay.
And the leak report that finally gets sent up if we have user consent is limited to a maximum of 512 kilobytes. So it's like all really small. So we really ensure that the footprint is very small, locally on a single machine, as well as across the whole Windows ecosystem. So we will talk about, Stephan will explain some of the policies that we have in place to ensure that the footprint is really small across the whole Windows ecosystem, right?
Okay.
In addition to the local machine. So the number one requirement was the tiny footprint. The second one is to ensure that the data that we collect is accurate enough that we can point to the source of the leak, right down to the variable in the function that is leaking, right? The third is to ensure that this data is sufficient enough that we could do diagnosis to find out what's the root cause of this leak, right? So we know there's a leak, and now we want to figure out what's the root cause of it, and we want to do this diagnosis automatically. So we'll talk about some of the automatic diagnosis, the heuristics that we have in place. So Keshava will talk about some of that.
Cool.
And the fourth, and pretty important, which is we want to collect the data so that we respect users' privacy, right? So we only collect function return addresses from stack frames. We do not collect contents of variables. We do not collect contents of memory. Right, so we only collect the function return addresses and the size of the memory block and the number of blocks and stuff like that. Okay. So no user data.
So just I want to ask one question, because there will be, Channel 9 has a really large audience. Yeah. Not all of them are developers. Right. And we never really talk about, conceptually, you know what a memory leak is. It means you just keep eating up a bunch of memory. But what I would ask is, what does that actually look like when you're looking at a variable? How do you know what it was supposed to be? In other words, just tell me, let's get to some point, let's talk about the morphology of a memory leak. What does it actually look like in the data that you get?
And in the, so there are two aspects of memory leak, right? One is, how does the memory leak look to the customer?
Sure.
Right? What are the side effects of a memory leak from a customer's viewpoint, which is really important to us.
Absolutely.
And then, how does this memory leak really look like to us from the report that we are looking at?
Yes.
Okay? So number one is from the customer's perspective. So a memory leak actually has bad symptoms, side effects. One is it has bad side effects to the actual application which is leaking, and it also has bad side effects across the entire system, in the sense that if the leak grows in size, the system could end up becoming really slow because the system is doing a lot of work trying to just pull pages in and out of the hard drive, for example. Okay, so we're consuming this bandwidth doing what we call as paging, which is may not necessarily be all the time useful to the customer, because this leak is not may not necessarily contain useful data. The second aspect of it is that if the leak persists and the memory pressure on the system persists, then this could lead to a degradation in the system functionality. So for example, if there's a critical Windows service or a process that's unable to allocate memory because there's not enough available, this could degrade functionality. So the user could see, for example, he right clicks on the menu button and he doesn't see many of the pop-ups. So he sees like a menu half drawn.
Yes.
He clicks on a window, he presses the start button doesn't show up for some reason. If it shows up, he clicks on an application, it doesn't launch, right? So many of these could be symptoms of exhaustion of memory, right? And and sometimes applications that are not robustly written, which do not handle failure of memory allocation requests, they might just crash. So user might just lose his data. So the memory leak per se is bad to the application as well as to the entire system.
Certainly.
Right. So this is the phase that the user sees. Now we are basically looking at it and saying, okay, so the user is going through all of this stuff. How does this leak really look to us, right? So a memory leak is when an application asks the operating system for some amount of memory, the operating system returns that amount of memory, right? So the application holds this memory and releases it whenever it feels to do so, right? So sometimes what happens is these applications lose the pointers that are pointing towards these memory blocks, and hence they don't free it. Sometimes they have the pointers and still they don't free it. So we look at these kind of blocks that the application got from the operating system but did not return back. So these are what we call as unfreed blocks, right?
Sure.
Blocks that are not freed with the application.
Okay.
So the report that we get back from our customer based on the user consent essentially contains two categories of leaks. Okay. The first category is the memory blocks that were unfreed by the application. Okay. And these are blocks that have no pointers to them at all, no references to these blocks, right? So we're saying, okay, so the application doesn't even have a reference, so there's no way that it can even free it, even if it wants to technically, right? So the way we do this is we run through what we call as the user mode part of the address space of the process, looking for pointers to all of the unfreed memory blocks. So during process termination, for example, when the process application is shutting down, we give the application a chance to clean up all the memory blocks, right? So the application might choose not to clean up certain blocks on its own, and certain blocks it may not be able to clean simply because there are no pointers to it. So we identify both. So blocks that have no pointers to them, which we call as leak blocks in the radar terminology, and then blocks that were unfreed but had at least one or more pointers. So the application might have had a chance to free it, but it still did. So we categorize them into these two blocks and package this data up and send this up to Microsoft.
Okay.
So when we look at it, we look at the variable and we look at the type of leak block that was there in the variable. And sometimes this variable, all the blocks that this variable used to allocate could all end up as being leak blocks, right? Sometimes you have a mixture, some blocks are leaked by the definition that we discussed earlier, and some blocks are outstanding, right? Outstanding as in there's at least one reference to the block.
Okay.
And then we have a heuristics engine that picks up this report automatically, diagnoses the actual call stack information, call frame information that we have in the report, and then finds the person who owns this code and files the bug automatically.
Excellent.
So because of the ease of use of radar, so even though radar was originally intended only for doing live leak detection, automatic live leak detection on the field, because of the very tiny footprint and the ease of use, a lot of teams in Windows and across Microsoft have started using radar in their regular testing and using the entire flow of automation, starting from detecting the leak to diagnosing the root cause to automatic bug filing, right? And so radar has ended up winning engineering excellence awards.
Congratulations.
The past 2 years.
Good.
And so the bugs discovered and fixed using radar have contributed to the reduced memory footprint in Windows 7 as well.
Yes. Nice job, because it's actually a smaller footprint than its predecessor, which is hard to believe because the kernel's bigger, but it's just amazing engineering. Cool. So there's other people in the room, I mean, obviously, so we're going to just turn the camera.
Yes,
This gentleman here.
I'm Stephan. I'm a developer on the Windows Reliability team. I've been doing the radar work for Windows 7. We have had radar as in the system since Vista, and in Vista, in Win 7, we added a few new features. Mainly, the one limitation we had in Vista, we could run leak detection only when the process was terminating. So if you attach radar, let's say, to Notepad, you need to wait till you close Notepad to get the leak report, which is great for short-running processes or applications, but it's a serious limitation for things which run a long time or never shut down. Things like IE, a lot of people never close it, things like the sidebar or services. And for those types of applications, we would not get leak reports. In Win7, we want to address those scenarios, which in some ways for the user are even more important, because a leak in the service host, there's no way to ever free that. If you have a leak in Notepad, you just close it and the leak will go away because the OS and process termination will clean up. But in the service host or Explorer, things which do not shut down normally, the leak will stay around forever. So what we use the new technology in Windows 7, which allowed us to make a copy of a long-running process. So you have, let's say you have a service host, and you can take a live copy of the user mode address space of that process while the actual process continues running. So basically you do a photocopy. And then you can do any kind of diagnosis you want to do in that copy while the original process continues running and is not impacted by that. So we do this now in Radar uses this technology for Explore, it uses it for IE, it uses it for services, makes a copy and then runs the leak diagnosis on that copy.
Excellent.
There's one small limitation when we run Radar on a terminating process. The terminating process has the opportunity to free most memory it wants to free. If you make a copy of a running process, there are obviously a lot more currently outstanding allocations because the process is still running. And as Baskar explained, because we distinguish between outstanding allocations, meaning a memory allocation which still has a reference, and truly leaked allocations where there's no more reference left, we can still find bugs on those truly leaked, not referenced allocations.
Interesting. So just one quick question, because I mean it could be confusing to people, just so that we make this absolutely clear. I mean, number one, there is a memory manager in Windows written by Landy Wang.
Yes.
So it's obviously rather amazing. But let's talk about when something terminates.
Okay, yeah.
There will be no memory still in use, right?
Yes.
That's
okay.
the point.
Yes. Okay. So, yeah, we probably should distinguish that a little bit. The memory manager is the component in the kernel which allocates and manages memory. It does the translation between physical and virtual memory, and then a process or application starts. The memory manager is the one handing out memory to the application. When that process terminates, the memory manager cleans up. No more memory is leaked. From an application perspective, the application normally doesn't interact with the memory manager directly anyway, because the way the memory manager works, it hands out pretty big chunks of memory, 4 kilobyte pages. If the application only wants to allocate a little string, it would not want to use a 4 kilobyte page because it would be a lot of wasted memory. So the application normally interacts with a memory manager and user mode, which we call the heap. That's a per application heap, and the heap interacts with the memory manager, takes those big pages and chops them off in little chunks. When the application says, hey, I need to create a C++ object, I need to allocate a little string, the heap provides that little chunk of memory to the application. If you write C or C++ code, you might use functions like malloc or free, new or delete, or heap alloc and heap free to get that memory. At that point, it's the application's responsibility to free that memory. It will be freed when the process terminates, because the memory manager just cleans up everything.
Sure.
But if your application doesn't terminate, or not very often, until you free your memory, it will stay allocated.
Excellent.
So if you have a little, let's say you write a program, and you have a little function which gets called frequently, and at the beginning of that function you need to allocate a little string, let's say an 8-byte string. You make a malloc call which goes to the heap. The heap takes some memory from its pre-allocated memory, hands it to you. If you forget at the end of that function to free that string, that little 8-byte allocation stays around in your process. The next time you call that function, you allocate another 8-byte string. So over time, those 8-byte strings add up, and they accumulate forever until your process terminates. And that's what the user eventually sees as Baskar pointed out, serious performance degradation. Finding that leak requires to keep track of those allocations, where precisely did they happen, what was the function where that allocation happens, and that what our radar does. So what radar sends back to us is basically those function names.
Okay.
And then at the back end, via our heuristics, and Keshava will explain more about this, we can pinpoint that function which has this bug, which did not free that little string. And then we can file a bug against the developer who owns that code to put that extra little statement in the code saying, free that string.
Use C#, man. Just kidding.
Use C#. Okay, there are
I'm just playing with you. But
there's a whole other bunch of
yeah.
leaks which are not leaks in our sense, but still have serious performance degradation.
Of course. Like just generating millions of objects and
millions of having big caches and never prove the cache. There are lots of other things here.
Absolutely, but this is very, very helpful. So you want to go to heuristics now, but there's also a big whiteboard that you kindly cleaned off. I guess it hadn't been cleaned for like 3 or 4 years.
At least.
Not quite
I mean,
long.
it's very impressive. Very nice. So shall we dig into the heuristics, the back end, or should we?
Yeah, sure. So there are two parts that we would like to cover. One is the heuristics part, which Keshava worked on to ensure that we diagnose the leak. I would like to draw the architecture of radar so we get a feel for what this whole thing looks like. And then Anthony is the person who has the charter for testing radar and making sure the radar itself is reliable and radar itself is robust and stuff like that. So Anthony will talk about some of his testing techniques that he used to ensure that he can get a radar that's reliable and robust.
Fellow Italian American in the room.
Correct.
Right on, man. So let's talk. So you want to draw pictures? We love watching them. Should we?
Yes, we should
meet this gentleman first, the genius in the corner. Hey.
Hi, I'm Keshava. I'm also a developer in the Windows reliability team. And I worked on radar. So the thing is, Baskar and Stephan just explained a part of the puzzle, right? So what happens on the client? So basically, radar kind of watches out for these applications that go over a certain threshold, and then radar asks our backend servers here at Microsoft whether this particular application is of interest to us or whether or not we want to perform leak detection on this application. So we internally maintain a bunch of rules to see what applications we want to actively pursue to detect memory leaks on, because we just don't want to indiscriminately go after every application out there. So we want to be able to manage that. So this allows us to be more aggressive during our own testing phase, and kind of be a little less aggressive and less intrusive to users. So once this request comes to Microsoft saying, hey, this application out here seems like it's doing something which consumes a lot of memory, are you interested? So we here at Microsoft have these rules, and we match up with these rules and respond saying, yes, go ahead, this is of interest to us. So once this response is received, radar goes ahead and performs leak detection, which Baskar and Stephan just explained. And what happens is radar generates this report, which is sent back to Microsoft. So back at Microsoft, this report needs to be analyzed. So there are these bunch of analysis servers that continuously open up these reports and analyze them. So how did we get to this part? Actually, the report getting till Microsoft was there in Vista. So in Vista, what happened was our developers, Baskar and Stephan, they used to look at these reports by hand and analyze them manually and detect these leaks. So we learned a bunch of stuff when we did this. So this knowledge was what enabled us to, we could leverage the knowledge that we had learned in terms of the kinds of leaks that were out there in the field, and what we had to actually do to detect the root cause of these leaks. So with this knowledge, we aimed at automating this and kind of scaling this upward so that we could really have a much, we could have a much more meaningful impact on the Windows 7 quality during its development. So we used this knowledge and we came up with this heuristic engine which would analyze these caps automatically without any human actually having to look at these reports and identify the root causes. So we analyze all of these reports that come into Microsoft from internal machines as well as from the field, from beta testers and all of these people, and analyze these reports and identify root causes. So we put them into two big categories. One, the leaks that we already know, and the others that are new and we haven't seen yet. So with these new ones, we run the analysis engine and identify the root cause. So we are able to we now have the technology to go ahead and pinpoint and say, this is the module and this is the function that is actually leaking, and we are able to open bugs at the other end. So opening bugs does not actually improve the quality of the product. They need to be They need to be acted upon.
Sure.
So we interact with the teams. They come back and ask us, and we help them run radar on their machines and try to repro the situation and try to understand what exactly is going on. And with all this information, they are able to resolve these bugs and reduce the footprint and have a better experience for our customers.
Sure. So I have a question though, because I mean, like I said, this is all, people know this by now. We cover Michael Fortin's team a lot, right? You guys do kind of, you do the work that most people don't see by design. They just see the results of it in an efficient operating system.
Right.
So one question I would have is, I mean, Bang Analyze is actually a software, it's a tool that is a root cause analysis tool in software that's pretty generic. Why wouldn't you use that on these cabs?
Right, so good question, and we have a nice canned answer for you. Radar does, the radar diagnosis is actually a Bang Analyze plugin.
Oh, beautiful.
So Bang Analyze is an overall infrastructure where several plugins can live. So there's one plugin that will analyze the root cause for crash, there's another plugin that will analyze the root cause for hangs, and radar plugin is analyzing the root cause for a leak.
Beautiful.
So in essence, we do use Bang Analyze framework. We plug it into that.
It's great.
And that's essentially how we do this. At the back end, it's basically Bang Analyze, which opens the cab, finds out which particular plugin it needs to invoke for that cab, and if it's a radar memory leak report, then it invokes a radar plugin, and then from then we take over, do the heuristics diagnosis, right up to the bug filing.
Excellent. And of course, we probably talked about that in the interview, but I do a lot of these. So, but it's good that we have to make connections.
Right.
So, perfect. Let's draw pictures.
You like pictures?
Yeah, I think it helps people understand what's really going on.
Okay, so this is the user system. So we have a monitor. So we have a radar monitor that runs automatically. So radar runs on all Windows Vista machines and Win7 machines, including pre-release code, betas, RCs, and RTMs, right?
Okay.
So we have a monitor that has a really small footprint that's running all the time, looking for suspected leak, right? So basically, it's looking for a potential sign of a memory leak.
Okay.
And so we have various processes that are applications that are running on the user's machine. And so when it detects a potential sign of a leak, so one sign of a leak is the commit charge of a particular process growing over time and reaching a threshold that is of interest to us.
Excellent.
Right? So when that happens, we basically then say, hey, okay, this process, and then there's a lot of other local policies. So there are policies that are stored locally on this machine that tells us how often we have done leak detection on this machine, how often we have done leak detection on a particular process are executable, should we even do it again, it's not been more than 6 months, for example, so things like that.
Understood.
So we have certain policies because we want to be really, really small footprint on the machine.
Now let me ask you a question. I mean, in your heuristics to figure out whether or not something is worth your analysis time, I mean, obviously, it's not like if application equals Internet Explorer, then obviously, because it's usually always the freaking problem, or the plugins that it's hosting.
Right.
But, and I should be clear about that, the plugins that it's hosting, I shouldn't be harsh to Internet Explorer team. So, what I'm asking you is, how do you determine? So you mentioned commit charge, blah, blah, blah. It's not like you know the name, you're interested in the behavior.
Right, so the behavior, yes, so there's behavior, and then there are properties of the behavior. And some of the properties that we are interested in is we look at how many hits across the world have we received from this application that says that this application shows a potential sign of a leak. So for example, in the case of Internet Explorer or any other application that you can think of, if that application has hit that particular threshold on several types of machines. By the way, we tune the threshold per machine. So the threshold is depending on the particular configuration of the machine. So we're looking at it and saying, wow, so throughout the globe, in the Windows ecosystem, this particular application comes up to be in the top 20 of the potential applications that could potentially have a leak. We look at this and say, wow, okay, this is something that we're interested in. So this is the stuff that I'm going to explain to you.
Perfect.
Okay. So this is essentially, so the radar monitor looks at this particular process and says, if it finds a particular process that's really interesting, it checks the local policies and says, okay, should I even do leak detection on this guy? Is this worth doing? And then once it determines that for this particular local user it makes sense, then if there is user consent, so by consent I mean if the user has opted in for the customer experience improvement program,
Sure.
then we basically send an URL to Microsoft that requests, hey, it says, look, I'm seeing a potential sign of a leak. Is this something is it something that you're interested in doing leak detection for, right? And these signatures of leaks are ones that we accumulate from across the globe, and then we say, okay, so this guy seems to be in the top 20 across the globe. We are really interested in finding out what's happening. Remember, the thresholds are tuned per machine. So the fact that this application is showing signs of leak across the ecosystem is already interesting to us, right? And the fact that it has a bigger commit charge by now is adding to the to the signature, right? So we collect this across the globe, and then we have heuristics that look at the top 20 of the applications that have this particular sign across the ecosystem, and we say, okay, you know what, we need 10 of these reports across the ecosystem. So again, I told you how we work hard to reduce the footprint in a local system, right, on a single user's machine. And this is how we actually work to reduce across the entire ecosystem. So for example, one application might have 100,000 hits, right, across the Windows ecosystem. We'll say, okay, we need 10 of these leak reports, right? We need 10. So across the whole ecosystem, only 10 customers will ever have to send this data, right, if they have accepted for the consent. So this is how we reduce the footprint across the globe, right? So we really work very hard to ensure that we don't expend too much of the user's resources. So once Radar Monitor determines that Microsoft is interested in this stuff, then we start another detector, which is now going to watch the particular process, target process, sys memory allocations and freeze, like how Stephan was mentioning, right? So this detector now knows the characteristic of this application. It also knows what it should do to this application. So for example, should it wait for the application to terminate, right? Or should it wait for some amount of time before it actually decides to do a leak detection on it, right?
Okay.
So in the case of, for example, if it's an application that will terminate, then we wait for the application to terminate, and after the application has been given a chance to clean up all its memory, then we go run through the user board process address space of it, looking for references and categorizing the blocks into leaked and outstanding.
Nice.
Right? But if it's a critical process, for example, WinLogon, or if it's a service host, right, any of the Windows critical processes that we know terminate only when you shut down, sort of,
Sure.
then we actually do take a snap of the process, or like how Stephan was mentioning, make a copy of it, run through the copy, and then figure out what the leak is. The detector then bundles this report up and sends it to Microsoft if the user has agreed to the SEEP, right? And as I mentioned, the LiDAR leak report is no more than 512 kilobytes in size.
Okay.
Right? And the leak report then goes through the whole automation pipeline. So we have the radar diagnosis. This is the diagnoser, which consumes the leak report and then produces bugs.
And runs Bang Analyze.
Right? And this runs inside Bang Analyze. So Bang Analyze is the bigger box here.
So with services, two questions for you. One, inside of your little policy, is the number one node the actual radar system itself, right? It's not like you guys are free of memory leaks. Have you ever caught any of your own memory leaks? What happens if radar leaks?
Interesting question. So this is something that, thank you for asking. So the monitor would report, so if the radar detector, for example, in Windows 7, for example, if the radar detector is crossing a threshold, then the radar monitor would inform us, and it would be one of the top. And so far, we have not seen it.
Really?
Thanks to
Excellent,
Anthony.
you guys. Of course, you guys are great developers.
But
obviously not.
our thresholds are pretty high.
Very high.
So Internet Explorer, because of the plugins, shows up a lot more frequently than Notepad.
Yeah.
You would need to have a very big leak in Notepad to ever show up. So the applications we normally run leak detection on are the ones you would expect. If you run Task Manager and look just at your commit chart, you see which ones are the top grossing applications. And those are the ones we most likely find leaks in, just because they cross the threshold first.
Interesting.
But in our own labs, in our own testing, we run radar on our own toolset to find leaks.
Yeah.
Good.
So Anthony will talk about some of the testing that he does.
Excellent.
Once we have the architecture here. So this is
Okay.
essentially the real flow. And as I mentioned, our focus in Vista and in Win7 primarily started off with doing leak detection for all the Windows processes and critical services and the Windows critical processes. And hopefully this is a technology that is something that would interest the wide audience,
Of course.
the ISVs, and hopefully we'll have some plan. We are looking at something that would help them take some of the leak detection through technology that we have built and maybe use it to find leaks in their own application. That's something that we are thinking about.
That would be, I mean, for example, in the canonical case of like an application like Internet Explorer that enables, COM objects written by God knows who to run in its process, in isolated processes if you're in certain tabs. But anyway, it would be nice if those applications could just say, hey, loading a plugin, keep an eye on this, or whatever. That way, quickly figure it out, shut it down, send information, move on. ISVs are like, okay, memory leak in this function.
Right.
Boom.
So we are basically thinking, we have something along the same lines.
Great.
We're planning, things are cooking.
We're thinking.
Things are cooking.
It's key to understand, everybody. They're cooking. Doesn't mean they're actually going to serve it to anyone.
Yes.
I don't want to get in trouble.
Right.
Cool. All right.
So, so the thing that is interesting now is to focus on some of the questions that you were raising, which is, how do we ensure that radar itself is reliable and robust and stuff. So these are things that Anthony, who is in charge of testing the actual technology, he can talk about and give us a flavor of things that he's been doing. Cool.
Do you want to start at the
Why
whiteboard?
don't we
Right on.
look at some of the whiteboard, because I think one of the really interesting things to think about in terms of how to test something like radar is to look at all the levels of abstraction that radar is working at, because we have some relatively complicated algorithmic stuff that's running within the context of a single target process. We have something that's running at the cross-process, multi-process level. We have stuff that's hitting the network and getting a response and interpreting that. We have, at the end of it, we're sending something up and hitting a whole nother pipeline. So, how do we make sure that all of this has high quality?
Mm-hmm.
And not only that, but whenever you have a tool that is supposed to be finding problems in somebody else's code,
Yeah.
it would be really embarrassing to have some really blatant errors in your own tool. So
Absolutely.
we want to make sure this is absolutely rock solid. So there's three things I concentrate on in the radar testing. So there's accuracy. We want to make dead certain that our leak detection algorithm has as minimal as possible false negatives and false positives. So a false negative would be when you do have a leak but we miss it. False positive would be when we say that you have a leak but you don't actually. So accuracy vital, reliability. When our monitor picks up the fact that a process is a potentially good target for radar leak detection, we can't really say much about what state that process is in. We don't know if it just started. If it's using a lot of memory, it probably didn't just start, but it may well have. It may be just terminating. It may be in the middle of doing some really complicated multi-threaded stuff that we want to have no side effects on. We want to make sure that we are robust in the face of problems communicating on the network, robust in the face of memory pressure ourselves. We've detected that there's a problem. There's already high memory usage on the machine, so maybe we are getting close to running out of memory. So we want to make sure we're operating sanely in those kind of conditions. So we want to be accurate, we want to be reliable, and as Baskar mentioned near the beginning, we want to make sure we have really high performance, because for some of these cases we're running code on the customer's machine. We don't want to suddenly make the customer feel like, what just happened? I didn't do anything, and all of a sudden my machine feels really sluggish. So the way I go about attacking these three separate issues: accuracy, reliability, performance. Is for accuracy, I break down the tests into basically classic testing methodology. We start looking at what are the inputs to our system, breaking them into what we call equivalence classes, looking for things that are on the boundaries between equivalence classes, and then devising test cases that test each of those. So for false positives, for instance, thinking about what may be some reasons that we might detect a leak that we say is there, but the developer knows is, for whatever reason, is not there. So, if somebody for some reason is storing their pointer to an allocation in a biased form, so meaning for some reason they allocate a big blob of memory, but instead of keeping their pointer to the start of the memory, if we just show this as a block, instead of keeping their pointer to the start of the memory, maybe for some reason on their own they're keeping a pointer 8 bytes in, 16 bytes in, who knows what. In this case, because they've biased the pointer like that, we are probably going to miss that. Or we may identify that as a leak, whereas they still know that when they free this, they just need to decrement their pointer back, and they're fine, something like that. So those are the kind of test cases I'm looking at in terms of accuracy. For reliability, there is a real strong tradition at Microsoft of eating your own dog food.
Absolutely.
We call it dog fooding, right? So as soon as we're able to in the development cycle, all of us on the reliability team start running this ourselves on our own machine on tons of different processes. So we are feeling many times what it's going to feel like for a customer to have this running on their machine, to get it running on real processes that are doing real work on real users' machines. Not only that, but we have other test systems. So we have certain stress test systems. We have another thing called long haul, which is where we run tests at a very long time interval, so weeks at a time. And it's almost like a stress test where the main thing that you're stressing is duration.
Wow.
And so I'm having Radar run in those. In the stress test, I'm running Radar constantly on lots of processes that are starting, that are exiting, that are doing crazy multi-threaded stuff with tons of different heaps, and doing as combinatorially complex a thing with heap allocations as you can kind of devise. And similarly in long haul, we're running Radar over weeks at a time on services to see, is there some degradation that happens at that longer time period.
No worries.
And then for performance, like Baskar has said, we have real concrete performance goals. So we are periodically looking at those, and if need be, also doing special projects. So like for instance, one thing I did during the Win 7 development cycle that was fun was, in conjunction with the client performance team here, they got a hold of a machine that has 192 gigabytes of physical RAM.
Nice.
So not the typical user machine, right?
No. Would be nice, but who knows, man?
Oh yeah, one day
Very
maybe,
cool.
right? RAM prices are dropping, I guess.
Ooh,
Sure.
that's pretty immense. So what?
So anyway, I did a study of, as we increase process size, because you already have server machines where maybe you have SQL Server running and it's using several gigabytes of RAM. As you increase process size up to even the 100 gigabyte level, how does Radar performance scale with those larger processes? And what does that mean in terms about what are maybe some processes that we want to ignore on a customer machine because potentially the price is going to be too high if the side effect of running Radar is going to be too high on a customer machine if we choose that process as one of our targets.
Okay, so that, you said a really key word, right? We've been very client focused in this interview, and in reality, out of memory on the server is a situation that completely sucks, because then you hurt tons of people trying to access the server. So can Radar run in the server environment? Does it run in the server environment? Is my question. I mean, of course it probably does, but
okay. So there are two parts to Radar itself, right? One is the part that identifies leaks and actively monitors the processes and looks for leaks.
Okay.
So that's the system that we described. Right?
Yeah.
But I explained to you what the side effect of a leak could be, which is all the bad effects that one could have, and the same bad effects essentially happen on the server side.
Certainly.
Only thing is now the number of customers that are seeing the bad effect completely explodes, right?
Yeah.
So on the server side, we do not really do this. So the radar leak detection stuff that runs automatically on all the machines only runs on all the clients automatically.
Okay.
So on the server, we do not have this particular technology running automatically. Nevertheless, the server code base that is being run. So there are lots, as I mentioned to you, lots of test teams across Microsoft now use radar in their regular testing to develop their server code. So that takes care of some amount of leaks that we could find here inside Microsoft during development and during the betas and stuff. But then there's a real situation out there, which is if there is a leak that escapes this net and goes out to the customer, then what happens? So there's a different piece of radar which detects memory exhaustion, like I mentioned to you in the beginning when I introduced my team. So we do have technology that detects that detects near exhaustion of commit charge on the system, even on server systems, and logs data that says here is the actual process that's consuming, and here is exactly how much it's consuming, and here are the page pools, and here are the non-page pool usages, and here are the tokens, page pool tokens, and what is the usage per token. So that information is logged for the top 3 consumers of commit charge, top 3 consumers of page pool, and top 3 consumers of non-page pool. So we log that event on the event. I mean, we don't have a user. Most of these servers are headless terminals.
Absolutely.
And so we log it to the event log, and then most of our customers have MOM service packs, and picking this up through MOM, this event through MOM, which says, hey, there's a resource exhaustion event that was logged by radar, and then the server, then people probably have ticketing systems that generate tickets automatically based on that to take action. So that's essentially what we do on the server side. Now the interesting thing that happens here is, the real reason why I started investigating the use of radar during Vista development was, we said, okay, Microsoft used to do leak detection earlier too in-house, right? So there were tools before radar that were being used in-house, but none of these tools were being used for automatic leak detection on the field, right? So the problem that we see is that the code base that we are looking at, even the Windows code base, is huge, right? And then when you put this on configurations of machines and configurations of applications and scenarios, the combinatorics really blows up.
Sure.
So it's normally not feasible to expect that we will find all the code paths. We'll test all the code paths and we'll find all the bugs in every code path, right? So that's essentially led us to the fact that, okay, in addition to doing this in-house during testing, it's extremely important to catch leaks in the field while it happens on the customer machine, right? So that was one of the original motivation for radar. And so this is, now that things go backward, because it's being used on the customer machine, because it's such a small footprint, people have started adopting this in-house and started using this internally as well.
Excellent. I mean, that's how a lot of great tools start. I mean, Watson, for example, began in Office. They only did it in Office. It was developed by the Office team, and now it's embedded in Windows. It's everywhere. It's the default way of pushing data up to reliable telemetry servers. I mean, so that's another example, which is very interesting. But one question I would ask is, do you guys have any way of knowing whether or not? So this question may or may not make sense. That's how I'm going to preface it. So with the kind of the excitement and necessity of virtualization, and again, this is a server side thing. If you have instances of operating systems running inside of virtual machines, the possibility of an application running inside of that VM taking up all the memory of the real system is impossible, right? So you would have to know that I'm in a virtual machine, we're not going to send any data, or we're in a virtual, does that question make any sense? Is that an issue that is interesting?
So it's an interesting question. There are two categories of answers to it. And I would like to cover those two, and then I would also like to talk about some of the leaks that we have seen, and and how we can avoid certain classes of leaks. So Stephan can explain some of the things. So Stephan and I manually looked at many of these radar leak reports, as Keshava mentioned earlier, in Vista time frame, and a lot of patterns of leaks emerged out of it. So I'd like to talk about that separately. But to answer your question about virtualization, so even on a virtual machine, even with with all the live migration stuff that we have built in place with the latest Hyper-V, the fact that a leak that persists in a virtual machine eventually leads to loss of data or loss of control, one of these two things, right? And so even with live migration and stuff like that, the fact is the leak will still be restricted to that particular virtual machine. And so the leak would impact the other systems and other services that are running on that virtual machine.
Sure.
So the fact that you're running on the virtual machine, sure, might reduce some of the impact, but the fact is you still have to go through the real disk, the actual disk, to page all of these things. So the problem that exists on a client machine also exists on a virtual machine as well.
Excellent. Okay.
Right. So and then I would like to transition to Stephan so that he can describe some of the problems that we have seen. For example, when you have a class member variable, right? And the member variable has two class variables inside it. So for example, class A has member variable B and C, which are of class B and class C, right? So if class A leaks, A, B, C, all three are leaked, right? So we take a lot of effort to actually make sure that we file a single bug, because the root cause for all of these three leaks is that class A was not freed, right? The variable of type class A was not freed. So we take a lot of pride in saying that we actually try to combine these three and say, look, the root cause for all of these leaks is one, right? Which is the A being not leaked, right? So there are certain patterns of leaks that a programmer could actually avoid. And Stephan should probably talk about some of the variant leaks and the COM leaks that we can actually avoid.
Perfect.
Yes, so as I pointed out before, the general pattern of leaking is that you allocate some memory from the heap via one of the standard heap APIs, and then you forget to free it somewhere. And at least when I started out looking at this, I would have assumed that most leaks are sort of, you do some complicated list management and somewhere your list gets corrupted or so, and then you can't free it anymore. Turns out from looking at the code bugs, at least inside Microsoft, most leaks are actually far simpler. You have a local variable, and you have maybe more than one return statement from your function. So you return at the end, and before you return at the end, you free the variable. But you also have a return statement somewhere in the middle. Let's say there's an error condition. And when you return from the middle of the function, you forget to free the variable. And this is a very common leak pattern. That often happens because codes live for multiple years and more stuff gets added over time, and people who modify that code don't understand all the implicit reasoning behind that. The other part is that when we test code, we might never actually test that error return statement in the middle of the function, because under normal conditions that error condition never fires. But when we ship out the code to people and customers, they run in different scenarios, and all of a sudden that error condition is true, and we return. And every time that error conditions happen, you leak a little bit of memory. So to avoid this, basically standard code pattern is have only a single exit path from a function. If you use C, you can actually use goto. If you use C++, and if you use exception, do proper exception handling, use smart pointers to avoid leaking local variables when you exit a function prematurely. That's sort of the most common one. Other common patterns are obviously COM reference bugs, meaning you have an allocated COM object, and you add some references, and you remove some references, and you get the two out of sync. Very common, somewhat hard to fix. Other patterns are, there are some COM-related helper structures like variants and B-strings, and there's actually a proper way of freeing them. Especially for variants, you actually need to use the clear function to free it. If you just reinitialize the structure, you leak memory. Other somewhat common scenarios are if you use C++ and you use C++ exceptions. If you throw anywhere an exception from inside the function, you don't catch that exception in the same function and one higher up the stack, you potentially leak all the local variables.
Interesting.
Because nobody had a chance to free them because the
exception happened.
The exception just moves it out, yes. Yeah. So if you use anywhere exceptions, you need to make sure that all your local allocations are either you catch the exception right away, or you have auto pointers, smart pointers, where you wrap all your allocations in and they're destructed, they're free, and those get called when you clear the scope. Other common scenarios, we have seen very few cases where global data structures. You have a global list and you don't clean up that global list.
Sure.
One scenario, which is often not a real leak, but actually the side effect to the user is a leak, that a component has its own cache. Let's say you have a component which renders bitmaps from the disk. The component might decide that it wants to read those bitmaps from the disk only once. because it's expensive to read them. So it reads them into memory and grows a cache, and then whenever that bit memory has to be referenced, it doesn't need to go back to the disk. It's actually surprisingly hard to have a cache which doesn't grow infinitely, because you either need to prune your cache, you need to decide when it's stale, or you just let it grow. And often software takes the easy approach to let it grow, which is fine in your little test case, because hey, you're testing those 200 bitmaps and it's fast. Once you have it in the field and people use it on lots of different directories, folder structures, you all of a sudden have a memory exhaustion because your cache is not bounded.
And it's worth pointing out that this is where Radar's ability to distinguish between leaked allocations and outstanding allocations really comes into handy, because the cache management may be completely correct. You know, they may have all of the pointers they need to, if they wanted to, free that memory, but they don't have the right policy in place to keep the memory usage bounded. So that outstanding allocation count for that cache just grows and grows and grows, even though technically speaking it's not leaked. But via the feedback we get from Radar, we can see, you know, these outstanding allocations have passed a point to where they're just completely ridiculous, and that in itself is
going to cause
it is its own bug.
Absolutely.
The other thing that Stephan mentioned is, you know, when there is a leak, the side effect for both the application and other applications could be a failure to allocate memory. Now, the failure to allocate memory itself would trigger you to go into an exception code path, right? So the fact that you're leaking memory leads to a memory exhaustion condition, which further leads to far more leaks, not just in your code, but in other code. So the failure to check for null reference pointers returns from malloc, for example, and heap free is a common problem. And most of the sometimes developers might think that, you know, hey, how often does it happen that, you know, with virtual memory management system in place, you know, how do I run out of memory? And now that I have 64-bit, my process address space is so huge, you know. But the problem is that when there is actual memory pressure, which is governed by the size of the page file and the RAM, right, combination of that. So when there's real memory pressure, because of a leak, it leads to more leaks. Because applications fail to check for null reference pointers, or even if they do check for null reference pointers, they take exception code paths, and the exception code paths do not clean up the memory, causing further leaks. So it becomes a vicious cycle.
And we have seen quite several bugs where that their leaks happened only when there was already memory pressure on the system. And as Anthony pointed out, those things are really hard to test, because in normal testing you don't experience memory pressure on the system, because you have an empty idle system and you test your one app. Your one app has plenty of memory, so it will never hit that code path where there isn't enough memory available. When our customers in the field run the same app, they might actually run 5 different processes at the same time, and if they're all high, big processes, all of a sudden you hit this scenario. And this is where Radar's getting data from the field really shines, because all of a sudden you can find those bugs which have a huge negative impact on the customers, but on the other hand, we never see them in testing here at Microsoft.
Excellent.
And when I originally started investigating Radar, one of the things that I really noticed was, so when the system is, so the kind of testing that application developers do to simulate out of memory condition is very localized. It's not global. So for example, let's say all we do is to instrument malloc and heap free, malloc and heap alloc, right? So that it returns a null, okay, to your application. Now, in reality, when the system actually goes under tremendous memory pressure, a lot of your dependent applications and services also undergo memory pressure. It is not just your application alone. So the localized testing of out of memory condition is really insufficient, in the sense that you really have to drive the system up, you have to drive the memory pressure up for the entire system so that you can truly catch bugs that result from out of memory condition.
Absolutely.
So if you just localize it only for your application by simulating, you know, the return values from malloc and heap alloc to be nulls, that itself turns out to be insufficient. So you have to go beyond that, over and beyond that, and say, no, I really have to drive the system up to the memory pressure, so that I figure out that if a dependency, if I had an RPC call that's outstanding, and if that call fails, or an LPC call that fails, then I take a completely different code path, which could be an exception code path, which I will not test if I'm only locally testing out of memory condition only for my application.
Certainly.
So this is something that is really serious for application developers even today, in spite of the decrease in the RAM cost and the increase in the size of the configurations. This kind of testing is important to ensure that the code is robust.
Absolutely.
And you can actually simulate that pretty easily. If you just go into your system control panel properties and set your page file size to 0. Then you have only physical memory left, which on a modern machine might be 4 GB. But then you bring a few big apps up and then consume most of the memory. Then you run your actual application you're interested in and see what happens when you start exercising it. You will see how funny it will react. Most applications, they will occasionally come up with certain error dialogues, which often do not make any sense because they fail at random points. And then you might often not get the dialogue anymore. It is a very interesting experience, and at the same time would be really frustrating to the user because it doesn't make sense at all anymore at that point.
Absolutely.
Yeah, it might be worth pointing out that, like I was talking about earlier with our stress tests, that one of the things we do on the reliability team in our own stress tests is we have processes that cyclically exhaust and release all the memory on the system, so that things like radar and some of the other things we have running there periodically experience that entire system-wide memory pressure, even memory allocation failure, and so that we can test how they operate under the kind of hard to predict circumstances that Baskar was and Stephan were both just describing.
Absolutely. I mean, the fact of the matter is that Windows and most other general purpose operating systems that have platforms associated with them are shared memory. Shared memory is the root of all evil. And in this case, I think it's a great idea for developers to test their application that's targeted for a shared memory system of what's my footprint look like for everybody else. Screw my own algorithms and everything else that I know I have to ship, but how am I impacting the system? We need a more kind of socialist or democratic or liberal development process where you think about the rest of the system as much as you think about yourself.
Yes. Right. This is actually also a pretty good reason why Radar is so successful, because we find leaks in shared Windows DLL, dynamic link libraries. And a lot of these DLLs are loaded in pretty much every process in the system. Let's say user32.dll, kernel32.dll, a small leak, let's say a kilobyte, in one of those DLLs, you might say, well, a kilobyte leak on a 4 GB system, who cares? But because the same DLL is loaded in dozens of processes, and if it has the same leak in all dozen processes, and 2 dozen processes, even a small leak all of a sudden has a huge impact. And then if we find those leaks via Radar prior to shipping Windows, we can actually have a huge impact, because all of a sudden we're not just saving a kilobyte or a megabyte, we can save dozens of megabytes on the system.
Excellent, you guys. Well, I'm taking up a lot of your time, which is awesome. This is incredibly interesting. So let's conclude.
So yeah, so today we saw a big portion of the Radar leak detection technology.
Absolutely.
Right? So of course this brought us very close to the resource memory exhaustion detection, which we alluded to with respect to what happens when your memory pressure goes up. But a part of Radar obviously looks at diagnosing and detecting memory exhaustion condition before they happen. So in Vista, for example, if you see a dialog box that says, your computer is running out of memory, and please close these programs, and there's a close and a cancel button there, that's something that's also being done by Radar. So when the system is about to hit memory pressure, that would really put the system in a bad shape. We actually go diagnose the problem, figure out, which particular application or process should be terminated, for example, so that we can reclaim the memory back. And we go and put this up to the user and say, hey, look, here's the actual application. If you want to close, press the button here, and we will go and do it. Because for normal users, just to find out why their system is behaving badly and which application they should even close to get back their system to a good state is very hard to do. So while on the back end we try to go and fix all the bugs that we could actually find on the field, we also put a safety net on the system itself to make sure that we protect the user until, while we're actually at it. Because the bugs that we fix today are restricted to the Windows processes, right? But there could be bugs in other code too that's running on the machine. So we need a way to protect the user from this and be able to let the user know, here is what you're suffering from, close here, and we will take care of the rest. Right? You reclaim your memory and the system is back. So Radar does that part of memory exhaustion detection as well on the machine, in addition to the actual leak detection and diagnosis that happens,
That's awesome, and I guess it's also important to note that when you were talking about patterns earlier, obviously the things that you guys learn, you actually stick into some static analysis tools so that, you know, developer X doesn't, you know, perhaps do the same thing again, because it'll be checked at compile time and be like, hey, you know, this, you're not freeing where you should be freeing, come on, or you're not, you know, the conditions you exactly stated, error conditions that probably didn't get tested, make sure you free before you throw.
Right.
So that's important stuff people understand. So you're helping software get better as well, software development. So you give yourselves a little more credit. So you're helping users, you're helping everybody, you're helping developers. It's awesome stuff, man.
We would let our customers and audience say that for us.
They will.
But you made an excellent point, which is that the value of the software in terms of improving the quality really grows if we can push the bugs out of the system much earlier in the pipeline. So what we are building now with Radar, as I said, we had Radar because we didn't have something that would run with such a small footprint with so much accuracy, right? Now that we have something running on the field, which is like a big safety net to catch these bugs, we are using that learning to push things ahead in the schedule. So now we are incorporating Radar in the regular testing inside Microsoft. We're also trying to see which of these rules can we actually take and incorporate it so that when the developer, for example, compiles his code, we actually go and find that leak right there when it's being compiled, rather than letting that code go through into the system and then being found either in regular testing or in the field. So we are basically taking this right down to the pipeline, so where it's really near to the developer, so that the quality is there right when the code actually gets checked into the.
Excellent.
And sometimes via education, because you know we try and make a lot of this, the kind of patterns we see as widely known as possible, so that not only does we push it up to compile time, but hopefully we push it up into the developer's mind so that it never gets written
in the first
place.
Of course. And I think the conditions you mentioned, the patterns, like you said, most developers, at least native developers, actually have to think about managing memory. That's part of what they do 50% of their job, unfortunately.
Yeah.
But the point is, they're not going to typically not free before they throw. What's going to happen is, like you were saying, giant code bases that get built up over time. I believe maybe you were saying that you can't actually get back to. Actually, Stephan said that, but you can't get back to, you know, understanding the 1,000 lines above.
The
right?
design intention is gone at some point.
Right.
Got it. But still, we all make mistakes, man.
Right, and I mean the key is now to figure out which is the thing that we are thinking is how to make this technology usable to other code that runs on top of Windows. Right?
Yes.
Independent software vendors and anybody else. So that's something that will be interesting to see if.
I hope that happens, because like a lot of the stuff that Michael's team does, when you think about diagnostics and troubleshooting and some of the stuff that's always running in the system, ISVs do get to see some of their problems. And typically some of those problems will eventually be memory leaks.
Right.
It's just they had this long kind of roundabout way to get them when they could have been laser-like surgery with your tool.
Right.
So not that it's going to happen, but I'm sure ISVs would love it.
This is something that is, that's a part
Right
of
on.
our day-to-day thinking too.
Cool. Hey, great to meet you guys.
Thank you.
Yeah.
Guys.
Fantastic work. Cheers.